Thanks a lot for having us on the program, and sorry I couldn't be here yesterday. I've heard there were some great papers. So this is a joint project with Paul and Tim, who some of you might have met yesterday. Paul is at UBC, Tim is at Bank of England. So the usual disclaimer applies. These are our own idea, and the BIS or the Bank of England has nothing to do with them.
You didn't come on the Eurostar?
No, I came with TGV. So this is a paper about monetary policy and wealth effects. So why wealth effects? Well, so as all of you here know, most of our macro models are based, the link between the interest rate and economic activity in our macro model is based on the intertemporal substitution effect, which simply states that as the interest rate goes up, agents find it more worthwhile to save, so they increase their saving and they decrease their consumption, okay? Now, and this holds both in the short and in the long run. There is no distinction between the two. Now, while we use it in most of our macro models, I think the profession has grown skeptical about the Euler equation and the mechanism underneath it. There is a huge literature that shows that the Euler equation is a very poor fit for the data. If you try to estimate the intertemporal elasticity of substitution, all the papers that have tried always find a number that is less than 1, and almost often is actually very close to 0 and insignificant. And this is a very old literature that goes back more than 30 years ago. Now, there is some more recent evidence on top of this that the relationship between interest rate and savings might actually not be always positive, but sometimes can actually become negative. So the relationship might not be monotonically increasing as the Euler equation would and the intertemporal substitution mechanism would predict. There is a paper by Nabar that shows that in China provinces, actually the provinces where the real interest rate fell more, so actually an increase in the saving rate. And there is a recent paper by Paul that argues that US households over time seem to have increased their desire to save, even though the real interest rate has been continually drifting down. So the question that we are asking in this paper is, what are the implications of all of this for monetary policy? So here is what we're going to do. So we're going to provide some suggestive evidence. This is very much a work in progress. So in the empirical part, we have started working on it. I don't think we have the silver bullet yet. So, but the evidence is going in the right direction. So we're going to provide some suggestive evidence. Then the impact of the interest rate on saving might actually very well be inverted, with lower interest rate increasing savings rather than decreasing them. And then we're going to present a model that features this, that is able to replicate this fact, and this model is based on retirement. Then we're going to study monetary policy in this model, and we're going to show that actually when we are in a world where lower interest rate increases saving, then monetary policy becomes very, very challenging. We're going to show a few results. We're going to show that there is a limit in this model to the degree to which the central bank can respond to inflation. That is, how much the central bank can be aggressive toward inflation is capped. There is an upper bound to that. We're also going to show that monetary policy loses potency, meaning that to engineer the same change in economic activity or inflation, larger interest rate changes will be required. We're also going to show you that while transitory interest rate cuts will always be expansionary, when these interest rate cuts are expected to be more persistent, they might actually become contractionary. And finally, we're going to show that forward guidance is weakened, and in some cases, forward guidance might actually be counterproductive. Now, so why wealth effect? Because the main message of this paper is that as we live in this environment, wealth effect becomes really crucial for the transmission mechanism of monetary policy. We're going to show that wealth effects can actually mitigate all these challenges that are introduced by this this relationship between this unconventional relationship between interest rate and savings. Okay, so why wealth effects? Well, okay, I think we all this is very topical because it kind of agrees with the evidence that central banks around the world are putting more and more emphasis on their impact on asset prices and financial conditions. If this is an extract from the December 2022 FOMC minutes, in which the participants clearly states that clearly acknowledge that monetary policy in their mind worked importantly through financial markets and asset prices. Also, if you take the recent paper by Anna and Annette, they show that the number of times in each transcript where FOMC transcript where stock market related words are mentioned is increasing over time. And this is not true only during periods of financial stress, where you might argue that the financial stability objectives trumps the monetary policy objectives, but also during normal times. Okay, so let me start with some suggestive evidence. Here we are starting by looking at the raw data. Okay, in this graph we plot the monthly combination of the saving rates and the 10-year ex-ante real interest rate in the US.
Sorry, can I ask one question?
Yeah.
So when we teach undergraduates, like at the two-period consumption model, we say that interest rate changes have contrasting income and substitution effects on consumption. In particular, when you are saving a lot, then a rising interest rate where the income effect will dominate, and you would end up saving less. So is that what you have in mind when you work? Is it this income effect or is it something else?
Say it again.
When in the two-period consumption model, when the household saves a lot,
Yeah.
and the interest rate goes up, the household will end up saving less because the income effect dominates the substitution.
Right. There is something like that. It's the retirement, it's a desire for retirement. I'll show it in 5 slides, but just to give you a preview, when you have to retire, what matters is not only how much money you enter retirement with, but also the future path of interest rate. And in that case, the income effect is the dominant force. There is no substitution effect. There is only income effect. Because if interest rates are high in the future, the flow income that you get from the same stock of saving is higher. So you need to save less. You would like to save less for retirement.
So what you call wealth effect is basically
No, the wealth effect is another part of the transmission mechanism. It's the fact that contemporaneous change in the interest rate, if the assets through which you are saving are interest rate sensitive, will change the value of the asset with which you enter retirement. And you show that these two effects will fight each other as retirement, as the retirement motivation becomes more and more important. Okay.
So what we call the inverted relationship is it's not just demand shocks versus supply shocks and effect they have on the price. So you'll say like if you have more desired savings, and if you represented yesterday have this mechanism, you have the analysis on this mechanism, you have a more desired saving, that's an increase in supply of saving, and that pushes down the price. And then you get exactly the slope that we showed you on the next slide.
Again, sorry, I was not here yesterday.
It's like a supply shock. It's a lot of supply shock that drives down the price. Is that what you have in mind, or like it didn't sound like
It is a supply shock. Wait, say it again. Go, start from again. Okay.
I think I had a similar reaction as Martin. I think it would be good to start with Michael 101. They have what they call an endowment income effect is the wealth effect in the standard formula. Because of effects are skewed effects. And these are the 3 effects that work here. And you put an emphasis on the wealth effect and the income effect.
Yeah.
And I think going to work that, and the other thing is we go from the interest rate to the saving rate. And I think she goes into the other direction.
Into the other, yeah.
We see a correlation on the previous one.
Right.
Not the cause and effect, right?
Absolutely. Yeah. Absolutely. We'll in the empirical evidence, I don't think we are at the level of causality to being able to pinpoint causality. In the model, there is the causality will go from the. I mean, it's going to be about the interest rate shock, because we really want to study how monetary policy how the transmission mechanism of monetary policy changes once you take into account all these three channels. Okay. All right. So let me start with. I mean, this is just looking at the raw data. As I said, we plot the saving rate in the US against the 10-year ex-ante real interest rate, and we color code the dots. This is monthly observation by groups of 4 years. And as you can see, from the mid 80s until the late 90s, a reduction in the real interest rate has gone hand in hand with a decrease in the saving rate, consistent with the intertemporal substitution mechanism. However, from the early 2000s, this relationship seems to change, and it becomes, instead of positive, it becomes negative. Further reduction in the interest rate, in the real interest rate, have actually boosted the saving rate rather than reducing it further. Now, while this is consistent with the idea that the link between interest rate and saving rate might be non-monotonic, of course, this is not evidence, right? Because this is just equilibrium equation. It might equilibrium outcome. It might very well be that in the second part of the second part of the sample has been dominated by demand shocks, and these points are just tracing out the negatively sloped supply of assets, right? So to further investigate this idea, what we can do is we can exploit the state level variation in the real interest rate and in the saving rate. In the following way, here we are regressing the state level saving rate on the state level real interest rate, which is computed as the US-wide policy rate minus the state level specific, the state specific inflation rate. And as you can see, if we estimate this regression from 2001 to 2021, which is that part of the green part of the curve that I showed you before, we indeed find the negative coefficients. And once we test whether this is coming more from interest rate or from inflation, it's clearly evident that all of the action is coming from the interest rate. Then we do something else.
So but the interest rate is the policy rate?
Here is the policy rate minus the state level inflation. So this is the realized real interest rate.
But then the interest rate varies only doesn't vary at the state level, of course.
The real, yes, it does, because inflation
No,
is.
the real, yes, fine. But then you said, it comes
Right,
from
right.
the interest rate, not from the inflation. But the interest rate is a
The nominal interest rate, yeah, of course, is common across the whole US. But it's just to say that the negative sign is coming mostly from the nominal interest rate rather than from different outturns in the inflation rate.
Right, but then the state level variation is not used to estimate that coefficient of -2. So you're left with the time variation, right? Then the kind of state dimension doesn't.
Right. Yeah. Yes.
So
Fair point. Yes. Yeah. Yeah. Sorry.
In column 1, the state variation comes from inflation.
Right,
Which could be due to, I don't know, balance assignments, all sorts of things.
or just demand shocks from consumption. I consume more, inflation is higher, my savings rate is lower.
Right.
No, but ours it only moves to inflation.
In this case, yes. Yeah. It's true. Yeah. Fair point. I think that's a fair point.
Do you have like bank level data on interest rates practice on deposits to us?
No, we're not at that level, yes. But it's a good idea. We could go down that road and exploit also that level of interest rate variation. Okay, we run one more exercise. In the model, as Martin was talking about, there is one of the prediction of the model is that when you enter retirement, it doesn't matter. It doesn't matter only the level of the wealth you enter retirement with, but also the interest rate that is operating on this stock of assets that you are entering retirement with. So here we are trying to test for that idea, and we are trying to understand what is the impact of wealth on consumption. So we are running this very simple regression in which we regress detrended per capita consumption on real wealth, again detrended per capita, and then we add the interest rate. As you can see, if we only include wealth in this regression, the fit is very poor, but also the sign goes in the wrong direction, right? It's negative. Only once we introduce the interest rate, then things starts to improve. The sign turns into the positive, becomes positive, which is what you would expect, and also the fit improves. But things really improve once you enter a squared value of the interest rate, which we do in order to capture this idea of the non-linearities of the non-linear impact of the interest rate. And as you can see, the fit really improved. Once we plot the estimated coefficient, we obtain what we. I'll be right back. What we also observe in the other graph, this C-shaped between consumption and the real interest rate. Yeah. Yeah.
So is this consumption or the consumption rate?
No, this is consumption.
No longer there.
Sorry?
Income is no longer there.
No, this is real consumption.
So why isn't income there? And also, have you controlled, also in the previous estimations, have you controlled for the food estimate? Because usually,
Have you controlled for?
for uncertainties. So in Europe, it's the unemployment rate, and something else, or whatever, which has an impact on the city.
Right. No, we haven't tried that yet, but it's a good point. We should really add those controls.
Measure of permanent income in that regression.
A measure of permanent income? No. Well, it should be wealth. Yeah. Indeed. Yeah.
Then we call it the modular.
I think what is the standard model would predict the standard consumption saving model is that the interaction is the key. So it depends on how much wealth you have, what is your effect on the interest rate. So it's nothing times are.
I see. Yeah. That's a good point. We should try it.
It would not be the interaction with the deviation from trend. It would be the interaction with stock. I think.
Yeah. It would be hard to. Yeah.
I think giving a kind of a structural interpretation to these estimates is a bit.
I agree.
You
I
could argue that
totally.
You're just estimating a Taylor rule.
Indeed.
Interest rate-
Although
interest
that
rate loads on the
it's
deviation of
it's
consumption.
true, but then that would bias to find strong effect on the linear term. It would go against finding effect on the non-linear term because that would be right. I agree. I mean, fair point. I'll bring them back to Tim. Okay. Yes.
I think yes, it's large literature on the consumption level. We have one impression focused on the number that stands there is that there is 4 cents on the income. That's the coefficient. You have more than double than that. That's good. So in consulted literature, Sidney Ludwigson and co-authors that work along this.
Okay. And you say that this is twice as much as.
It's the standard estimate.
I see. That's a good point. We'll take a look at that.
The standard estimate moves over time with each new income. Still, they have double than the standard estimate.
I mean, controlling for income is one thing. Different type of errors is the other thing.
In physics, there was a standard estimate in the 19th century physics, and that been divided by 10 100 years later. There was a lot of consensus, and nobody tried, dare deviate from the consensus. So this physical constant was overvalued by a factor of 10 during 100 years, just because of consensus.
All right. Thanks. Look, bottom line, as I said at the beginning, we just started looking into this. We think that these suggested evidence justify looking at a model in which the relationship between interest rate and saving might actually be inverted, negative rather than positive. Of course, as I said, we don't have the silver bullet yet to argue that that's definitely the case in the data, but we think that the evidence seems to suggest that we are going in that direction. Now,
Definition of question. So what is the definition of real wealth?
real wealth, that's, I think it's just financial wealth. I think it's just financial wealth in this case. Yeah, financial assets, yes. There is no way to account for human wealth, human capital. I don't think we've done that yet. Okay, that's it. So as I said, we're now going to look at a model that can replicate this inverted relationship between interest rate and saving, and this model is based on a retirement model. So we're going to take a very standard new Keynesian model, and we're going to augment it with a Blanchard-Yard structure and the retirement model, Salagher, 1999. So how does this work? So the agents in this economy can be in three different states. Can be working, can be retired, or they can be dead. So they start their life in the working stage, and every period with probability delta 1, they have to stop working. Once they stop working, they can either retire with probability Q, or with the remaining probability, they just die directly. Okay, so no, they don't have time to enjoy retirement, they go directly to the tomb. Once they are retired, there is a probability, every period they face a probability delta 2 of dying. Okay? Now, once an agent dies, either from retirement or from working, is replaced by a new agent that starts in the working stage, so the fraction of agents that are actually working is constant at every point in time. Okay, so let's study the problem of a household that face this retirement problem, and it's instructive to start from the end. So this is the problem of a retired household. So once retired, the household only receives income from the income stream generated by its stock of assets. So basically, he has deposits, a bunch of deposits in the bank, and these deposits earn the interest rate, the real interest rate RD, and he just have to choose how to allocate, how to consume out of these savings that he has. Okay? Now, the optimality condition tells us that the consumption of these retired agents will be a function of its stock of assets, ART, times this function gamma. And this function gamma simply captures the value, the entire future path of the interest rates that are working on this stock of assets. And as I was explaining to Martin before, why is this important? Because it doesn't only matter how many assets you have, but how much income flow you will earn in the future from this stock of assets. Okay? So just to give you an example, if sigma is greater than 1, then higher interest rate in the future imply higher income flow from the same stock of assets in the future, which will increase their demand for consumption, which will increase their consumption, which will reduce gamma and increase their consumption. Okay? So this is the problem of a retired households. Now, going back one period in life, one step in life, this is the problem of a working households. Here we assume that working households own all the firms in the economy, and once they retire, they just liquidate these firms, and they start retirement with this stock of wealth. Okay? Now, so the problem of the working household is slightly more complicated because they have to choose not only consumption, but they also choose how much to work. Okay, and this is the static decision. And in the future, you know, they with probability 1 minus delta, they will still be worker tomorrow. with probability delta 1 times Q, they will be retired, so their value function is the value function of the retired agent. And the stock with which they start retirement is given by their savings, the deposit that they have in their banks, plus the N, which is the liquidation value of the firms that these households own. Now, the only thing you need to notice here is that instead of working with QT, we are working with QST, meaning that where QST is the subjective probability of surviving the retirement shock. And you'll see why we work with a subjective probability rather than an objective probability in a couple of slides. Okay? So now this is the optimality condition for the working households. Of course, you have the static labor supply equation, and this is the Euler equation of the workers. As you can see, compared to in a conventional model, you would have only this part, right? This would be only the future consumption, future consumption, and the current interest rate are the only thing that determines current consumption. But once there is a retirement stage, once there is the probability that this household enter into a retirement stage, there is an additional term in the Euler equation, okay? And this is coming from what we call the retirement effect. We will unpack that retirement effect once we log linearize, just because it's easier to see. But let me just say...
What's going on there? Because before the retired value function only had assets as an argument. Now there's the second argument. What is that?
No. The retired has gamma as an argument also.
Not up there.
Not up there.
Oh, sorry.
Sorry.
Well, this is the solution. Yeah. Sorry. This is the... Yeah, we should have used different... this should be indexed by T, and then you can see that the only thing you need to keep track, these are the sufficient state variables in this problem. That's just bad notation. The value function of a retired household depends on the stock of assets and gamma. Where gamma solves this equation here, which intuitively captures all the future expected future path of interest rates. Yeah?
This is a sort of pseudo value function. It's not a sole function of the current state, the current A, and the current shocks.
It's a function of your individual wealth, individual state, and an aggregate state. You need to know something about this economy. And the thing you need to know
about this economy is summarized by the current realization of the shock.
No. The thing you need to know...
Gamma itself depends on the state.
Yes, it will. It will be sure. Once you have like your Markov representation, yes.
To be sure, what if the interest rate follows the random random?
Yeah.
How does this function collapse?
Well, then the expected one is constant, so you can solve it analytically, but it will still be a function of the expected. It's just that the expected interest rate is constant.
So it's the current interest rate?
Yes, yeah. So you're considering like fully permanent interest rate shock. Yes, you can write it as a function of the current interest rate, but the message still remains, right? When sigma is greater than 1, higher future interest rate will increase the value of your saving and therefore boost your consumption or reduce your desire to save. Okay? Whether the interest rate is constant or not only determines whether you can solve for this analytically.
What I find strange about this formula down there is that for log preferences, the interest rate has no effect.
Yeah.
Your value should still increase with the interest rate if you have financial value, right?
Yes,
So
because it's in
savings
here.
will
It's
not
in
be
here. It's in
affected?
here. It's in here. It's embedded in alpha in A tilde. A tilde is your stock today times the interest rate. Okay, so this is the beginning of period.
Fine, but if you know that all future interest rates will be higher by 1%, you're much better off from given stock of wealth. But in this formula, in log preferences, that wouldn't appear.
Yes, they would drop out.
It shouldn't. Anyway, let's talk about
It shouldn't. Okay, yeah, I haven't explored that case, but it's let me think about that. Okay, so to understand how the retirement effect affect this decision, as I said, we will unpack it soon. How much time do I have left? Wow. Okay, let me look at the steady state asset demand, which is the steady state Euler equation. As you can see, the relationship between the interest rate and the steady state level of asset and the steady state asset demand is non-monotonic. There is one region in which it is positively sloped. This is the region where the intertemporal substitution effect dominates. Higher interest rates are associated with a higher demand for savings. And then there is a region in which the relationship is negatively sloped. This is the region where the income effect dominates, the retirement effect dominates. Lower interest rates now are associated with higher demand for saving, exactly because of the mechanism I just described. Okay? So this is just to give you an idea of what the retirement motive introduces in this model. It can generate the negative relationship that I was talking about in the introduction of the paper. Now,
Maybe I'm missing something, but not the standard IRI model, where these models will also get this thing for low level of interest rates. So if you plot the assets supplied by households over the interest rate, then you will still get this shape up there, even if retirement there. So maybe I'm missing something.
sure, we don't claim that retirement is the only way to generate this downward, this inverted relationship. We said it's a possible way of doing that, and we chose that. We chose that to start with. Maybe there are other ways of doing that, which are empirically more relevant. I would think that retirement motives it's actually quite believable, no?
Still don't get it. So in the previous slide, we have in a standard model with retirement, we have a standard order equation. You write down
In a standard model without retirement. Without retirement.
With retirement, a plain vanilla household model with retirement, we get a standard Euler equation without the second part. Now, what in your model with retirement is different from a standard model with retirement, so that in the Euler equation, I get this discounted term. That I don't understand.
What would be a standard model? In the assumptions that I told you, what would be different would be different in a standard model?
What assumption do you make on, if I write down the household retires and then there's no retirement income, it just consumes down his wealth in retirement.
Yeah.
I look at the first order condition, I get a standard Euler equation without any additional term.
Without this additional term.
The standard model doesn't have it. So what
Is it because you're looking at log preferences?
No.
I don't know.
The standard first order condition is saying I'm moving consumption from today to tomorrow, I get a standard Euler equation.
But this is because he substitutes for consumption in retirement from the optimal consumption in retirement.
Yeah, I don't understand your. What do you mean it's not there?
The right-hand bracket is, you could replace it by consumption in retirement, right?
Look, let me see like this. Like in you're working, your future, in the future with probability 1 minus delta, you will still be working. So this is your part of the future, right? But the probability delta, you will be retired. So here, you should consider the value function of the retired agent, right? Does this make sense? I don't think there is anything.
You could substitute, however, for consumption in retirement there, and then it would just be something like a
Sure.
normal Euler equation.
Sure.
Is equivalent.
Sure.
I suggest we give you a little bit of slack for the next 5 minutes to get to the model, and I give
Yeah.
you another 2 extra minutes to present, and then we're all done in 8 minutes.
Thank you. Okay, so then we close the model. Everything else is very standard. We have a standard New Keynesian. Machinery for the Phillips curve. Now, the asset structure of this model. As I said, it's very simple. There are banks, the households deposit into these banks, and these banks invest in 2 assets. A short-term assets, which you can think of it as central bank reserves, so it pays the policy rate, and then a long-term asset, B, which is simply a real perpetuity with a decaying coupon, and the price of this asset is Z. Okay, so it's very standard here. All right, let me close the model. Asset supply is constant, so the amount, the short-term and long-term assets are in constant supply. An important parameter here, which you'll see in the future why it matters, is the share of long-term bonds in this economy. This is a steady-state share of long-term bonds over the total value of assets in the economy. And finally, monetary policy is set by a simple Taylor rule in which the central bank responds to expected inflation, deviation of expected inflation from trend. Okay, to solve the model, we make one simple assumption. That's why the households work with a subjective probability. We only care about the introduction of retirement motives. We don't really care about retirees. So what we assume here is that basically these agents never retire. Whenever they stop working, they die. But these guys think that they will retire, so they save for retirement. Okay? This is just to simplify the algebra, and actually for people of my generation might actually not be a bad approximation of reality. Okay, so let me show you how the equilibrium changes as we vary delta 1. So this is the equilibrium of the model. This is a steady-state asset supply. This is the steady-state asset demand, which coincides with the asset demand of the workers, because now there are no retirees. If we are in a world with low delta, that is with a low probability of enter the retirement stage, that is there is a low, the strength of this retirement motive is very low, then we are on the upper branch of the asset demand curve, okay? Where the relationship between, where the intertemporal substitution effects dominate. The relationship between interest rate and saving is still positive. As we increase the retirement preoccupation, as we increase delta 1, then we shift, the equilibrium shift on the asset demand shifts up, and the equilibrium shifts on the lower branch of the demand curve, where the relationship between the interest rate and saving is negatively sloped. Okay? This means that there is a threshold value for delta 1 below which we are in the upper branch and above which we are in the lower branch. And that's exactly what we are going to look. We're going to study how the transmission mechanism of monetary policy changes as delta 1 increases. Okay? Just for reference, if delta 1 is 0, then we are back into the plain vanilla New Keynesian model. Okay? There is only intertemporal substitution effect. Okay? All right. So first of all, okay, let me unpack the transmission mechanism. But we discussed it before. Output today depends on a weighted average between two effects. So the impact of interest rate on economic activity depends on the conventional intertemporal substitution channel, and it's captured by here. In the retirement, once we add the retirement stage, however, there are competing effects. On the one hand, these two terms here capture the income of the impact of the interest rate on the flow of the assets in retirement. So this means that as the interest rate goes down, a reduction in the interest rate will actually reduce demand, right? This is coming from the retirement, from the income effect of retirement. But then there is an additional effect and work in the opposite direction compared to the conventional intertemporal substitution effect. But then there is this wealth effect. There is also an effect that the interest rate will affect asset prices today, and therefore the value of the stock of asset with which you enter retirement. Of course, the strength of this channel, which again work in the conventional way, higher asset prices boost consumption, depends on eta, which is the share of long-term asset in the model. Why is that? Because the long-term assets are the only interest rate sensitive asset. If there are only short-term assets, then there are no wealth effects. Okay?
It depends on the maturity of the asset.
It depends also on the maturity.
Of the retiree.
Sorry?
It depends on the maturity of the assets relative to the maturity of the retiree.
The wealth effect, like the impact of...
How long does a retiree live relative to the bond?
But the impact of the interest rate on the bond, it doesn't. Okay. All right, so eta captures the share of interest rate sensitive asset in the model. When eta is 0, then there are no wealth effect in this model. My goal is to understand how, to convince you that having a high eta is actually very important. Why? Okay, so let me just, how many minutes do I have?
You have 4 minutes.
4 minutes, okay. Let me just show you this. This studies the region of determinacy and indeterminacy of the model. On the x-axis, you have delta 1, okay? And on the vertical axis, you have phi, which is the Taylor coefficient in the Taylor rule. As you can see here, for low level of delta, if we start from here, then we have the usual result that any value of the Taylor coefficient that is above 0 delivers a determined equilibrium in this model. However, as we cross the blue line, which separates the upper and the lower branch of the demand of the asset demand curve, and delta 1 increases above this region, then there is an upper threshold on the value of the Taylor coefficients that deliver a determined equilibrium. Okay, in the black area we have indeterminacy. Okay, so why is that? Well, the best intuition I can give is that there are competing forces in these models, right? In this model, right? And in order to have a determined equilibrium, you need one force to dominate the other. Okay, and here we are looking at a region of the state space in which suddenly the intertemporal substitution effect becomes weaker, and it's replaced by a competing force, which is due to the income effect for the retirees, right? To compensate for this change, we need strong, which works in the opposite direction. To compensate for this, which is strong, we need stronger and stronger wealth effects. In fact, this plot is done for a share of long-term bonds of 50%. If we increase that share, then the black region shrinks and monetary policy is less constrained. If actually we reduce the share of interest rate sensitive asset in this economy, the black region expands, posing a more severe constraint on the ability of the central bank to fight inflation. Then let me look at monetary policy efficacy. This is the impact of an interest rate shock on output today, and we can prove the following result. As delta 1 increases, the impact of monetary policy on output and therefore inflation falls. And this is always true, regardless of the strength of the wealth effect. That is, regardless of eta. However, when eta is low, when the wealth effects are low, this decline is stronger. We can also show that in the lower branch, that is when delta 1 is above the cutoff value, now a lower interest rate remains expansionary when the persistence of the shock is low, when the shock is transitory, but it becomes contractionary when the shock is persistent. And the cutoff value on the persistence of the shock is affected, again, by the strength of the wealth effect. The weaker the wealth effect, the weaker this cutoff. That is, the more likely that an interest rate shock is contraction. Okay? And the stronger the wealth effect, the more likely is that the same interest rate shock is expansion. Finally, forward guidance. This is considered like the usual forward guidance exercise. At time 0, everybody knows that at time t, the central bank will reduce the interest rate for only one period. This is the impact of such an announcement on output today. Okay. In the conventional model, you will only have this term, right? The effect of forward guidance, the effect of this announced monetary policy expansion, it's fully anticipated to today. Y0 is equal to YT. This is how forward guidance changes in this model. As you can see, these, for values of delta 1 that are different from 0 and 1, this is positive. This term is positive, meaning that if there is a positive shock to the interest rate, then output will fall at time t, but the fall at time 0 will be less. Okay, so this the introduction of retirement motives can solve the forward guidance puzzle. But more interestingly, I think, is that the forward guidance can even be counterproductive. That is, we can have situation in which this announcement, even though it has the expected impact on output at time t, it has the opposite impact on output at time 0. So if you announce that you're going to cut the interest rate at time t output will rise, but at time 0 output might actually fall. And this is proved here. This occurs again when the retirement motives become strong, that is delta 1 increases, and it's also more likely when the wealth effects are weak. That is when eta is low. Okay, I think I need to conclude, right? Okay, so let me just summarize with this. We have provided I hope I managed to convince you that that in this model, once we introduce retirement preoccupation and retirement motives in the conventional model, this alters the monetary transmission mechanism substantially. The monetary transmission mechanism moves away from intertemporal substitution and towards wealth effect and asset prices. Okay, and this has important implication for the central bank. Monetary policy becomes more challenging in this environment. The central bank can't respond too aggressively to inflation. It requires greater interest rate volatility, and this will have a repercussion for financial stability. And even forward guidance might actually not work, might actually become counterproductive. Wealth effect in this environment, wealth effect becomes crucial to mitigate these challenges for the central bank. This has also implication for the asset supply and the composition of assets between short and long term, but I need to stop here.
Yes, we're unfortunately out of time. We have no time for questions either. And
thanks.
after that,